forget, next Tuesday you guys will be talking to the class and not I, right? From then on. So next Tuesday will be lecture 17, 18, 19, 20. So the last 4 lectures are your lectures, and you can impress your fellow co-students. Okay? I can lean back, I can take it easy, I can sit there and I can listen to you. I look forward to that. Again, you are invited to swap with others if you want to. I don't need to know, right? As long as you guys make it clear among each other how that should work. Just the way I have it down for Tuesday, the people I have down alphabetically ordered right now are still Chandler, Dawson, Doherty, and Griffin. And I know that Kevin might want to swap with someone. So, and again, it's up to you to choose, the medium of presentation. You can choose, just like I do, use a board, use a PowerPoint, or whatever medium you prefer, okay? Whatever makes you most comfortable. And I also suggest that you give your little presentation at least once to yourself, better even to some of your buddies, okay? So you see how quickly 15 minutes actually go by when you give a talk. 15 minutes, probably 10 slides at most if you use slides. With at most 25 words per slide, not more. If you use more than 25 words per slide, then that's more than one slide. You have to break, okay? You like those slides where there's like 1,000 words on the slide? Not good. Okay, so I would like to hit on 2 things at the beginning. Just very briefly, even though you won't be doing this as part of any of your projects, unless you choose it for your final project, I would like to talk on the volumetric version of Lawson's algorithm for constructing triangulations or tetrahedrizations in space, 3 space. And I would like to hit on the Sibson interpolant over polyhedral complexes in 3 space, okay? How that works. Just briefly, so you have heard about it. So there is Lawson's algorithm. And the whole idea behind, or the purpose of Lawson's algorithm is to construct a triangulation that maximizes the minimum angle in the triangulation that results, which is a delaunay triangulation. Okay, those definitions are equivalent. The definition of a max-min angle triangulation or tetrahedrization, and the definition of a delaunay triangulation or tetrahedrization. And so Lawson's algorithm is building these triangulations one by one and inserts vertices one by one, right, Marina? And then during each step, it figures out whether I connect things properly or I could do better by reconnecting. Okay, that's the atomic step is always to perform edge flips. That was the atomic step. Lawson's algorithm and the way it was called in his day and age, constructs a max-min triangulation, constructs a max-min angle triangulation, maximizing the minimal angle triangulation, max-min triangulation, right? A triangulation, or, excuse my symbolism, tetrahedrization, okay? Tetrahedrization, okay? That word tetrahedrization actually doesn't exist, even though you will find it in papers, okay? It hasn't made it yet into the dictionary, so therefore it doesn't really exist officially. But just use it over and over again, and in 100 years it will be an official word. So and the basic idea is the atomic step in Lawson for the volumetric case, for tetrahedral case, okay, so in 2D it worked like this. In 2D we had this configuration to compare against the alternative, and the alternative is that, right? And the better of the two is this one. So what is the equivalent configuration we have to consider for tetrahedra? Here we consider 2 triangles and determine among the 2 possibilities And in 3 space, what do we consider for tetrahedral meshes? We consider how many? 2 or 3? 2? 3? 2 tetrahedra. Okay. 2 triangles share an edge. 2 tetrahedra share, if they share something, they share an edge or a face. So we share a face here. Okay? So say we have 2 tetrahedra happily sharing a common face. Okay. So this is one configuration of this polytope, and I indicate that these 3 guys, these 3 vertices in this mesh, define the shared complex, subcomplex, this triangle, right? So this is a shared creature, okay, of 2 tetrahedra. Okay. Okay, so these are 2 tets. And then, okay, this is the alternating pattern, right? From this to that, from that to this. What happens here? Here I swapped the shared edge from this edge to this edge, and here I have a shared face, so obviously you have to swap a face, right? Or how do I swap this face? It's just two states sticking on, right, on top of each other. So what do you swap there? You cannot do that. So the swap configuration is one where you replace the shared face by a shared edge. Okay? So a 2-tet configuration becomes a 3-tet configuration. And so the polytope, this convex region in space, remains the same, but it will get tetrahedralized in a different way. Not by 2 tets, but by 3 tets. Where are these 3 tets? You ask me. Okay. This is this polytopial region there. And I want to tetrahedralize it with 3 tets. Where are those 3 tets? Right now there are no tets. Okay, right now there are only the bounding faces of this strange region. Here I drew it as tets, right? The outside faces in this interior shared face. But where are the tets here in the interior? Okay. Okay, I have to see this for the first time. This becomes a swap, okay? Now you see the 3 tetrahedra there? They go around this axis in the middle. Huh? You see the 3 tets? First tet is this guy. Boom, 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 boom. Next tet is this guy. Boom, 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 boom. And the last tet in the back is this one. Bop, 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 bop. So these are like 3 skinny tets that go around this axis and share this edge. It's a shared edge. Okay. So this is a flip operation. A face becomes an edge, or you can do the other way. This edge of a 3-tet configuration becomes a face. So that is, of course, the generalization of that. So 2 tets become 3 tets, or vice versa. So in 2D, you had to search for convex quadrilaterals, right? These configurations, and determine which one is the better of the 2 possible triangulations. You could not do this for non-convex configurations like this. There is only one way to triangulate it, right? This way, boom. That also means that this polytope also must be a convex one, right? Otherwise, you keep it the way it is. You cannot tessellate it the other way. Okay. So this is the atomic operation for Lawson. Again, you would start with one big tetrahedron that contains all the sides that are given to you that you want to triangulate. The word triangulation is used for all dimensions in general. Okay, so that's the mathematical way to deal with it. Triangulation is triangulation, whether it's triangles in the plane or it's tetrahedra in space and so on. Triangulation applies to all. So you want to triangulate space with tetrahedra that have the largest possible angles. So first you start with one big bounding tetrahedron that contains all the sides, and then you insert all the sides one by one. And at every step of the insertion, you just first connect a new side to the 4 vertices of the tet that contains it, and then you make this check, right? Can I improve the quality by doing either the swap from here to here or from the right side to the left side? And you do that until you have inserted all points, and then you are guaranteed to have a max-min triangulation. So far, so good. That's that. And then I also want to talk about Sibson for volumes. Sibson's interpolant. Interpolant for the 3D case, for 3D or say trivariate case. Trivariate case. Hard for me to draw, so I can only draw tessellations that are a bunch of cubes. Example, tessellation, a Cartesian, right? Cartesian tessellation would look like this. If your sides were the grid vertices, the locations of a Cartesian mesh, then this could be a valid Voronoi complex, right? Of this. It's perfect cubes that are surrounding each vertex of a Cartesian mesh, right? That would be a Voronoi diagram, a Voronoi complex for regularly spaced locations coming from a Cartesian mesh. So the tessellation would consist of these cubes. And on the boundary, they go to infinity. That's fine. And so if you have this type of a mesh, we have to worry about evaluating or constructing the values of the Sibson interpolant over such a polytope decomposition. So to compute the Sibson value, at a location, an arbitrary location, at a point P. Again, we pseudo-insert it into the complex, and we have to compute certain subvolumes. Pseudo-insert, insert P into the diagram or complex. And compute subvolumes. Volumes serving as weights. Serving as weights for the Sibson interpolant. For Sibson interpolant. Okay, so how would this look like if I just focus on one perfect cube tile? These tiles are polytopes, convex polytopes, with planar faces, convex polygons surrounding, defining the boundary of those convex faces. Okay, and so this is one tile. So this tile center would be here, right? So this would be a point xi, a side, an original side, and I have a function value there, function value fi. And now I want to evaluate, for raycasting or whatever, evaluate a function at an arbitrary location, x by z, an arbitrary point, and I put this point here. Okay, that's an arbitrary point P. And so again, this is just one tile, one cube that's surrounded by a bunch of other cubes, right? I just cannot draw them. And so when I pseudo-insert this point P into this complex, then it will cut away a certain chunk of this volume, of this tile. This is a tile I, this cube, belonging to point xi, original site xi. Well, I insert this evaluation point P in a pseudo fashion into this complex, and then of course I will cut away a chunk of this perfect cube. And so it will probably look like this. Okay, the way I've done it, it will cut away a little left chunk. We cut away a little chunk to the left, which would be part of the tile for P. And so this area now, this cutaway chunk, I would call it a volume chunk, volume I, because it's a chunk of tile I that is being eaten away. So, and now I have, of course, these chunks of being taken away or cut away from all the other surrounding original tiles. So this particular point has an influence on this point via its function value and via the size of this cutaway portion of its tile. So the overall value of Sibson at P will be the combination of all these function values in the neighborhood of this tile stencil, where the function values of the tiles or the sides are multiplied by these volumes. So you have a combination of, say, there are k of those tiles, I from 1 to k, and the volumes, the subvolumes of the tiles serve as weights of the function values in those original tiles, and then you divide by the weights, the volumes. It looks nice and beautiful, actually, to do it. I myself have never programmed this, okay? It becomes very complicated and expensive, but this is a generalization, of course, of the formula that you do for assignment number 3. But handling these arbitrary convex polytopes, data structure-wise, is not easy. All right, so that is triangulations, tessellations. Who is done with project 3? Nearly done. Who has started? Good. Yeah, depending on how you implement that with a very clever and very nice and elegant data structure or not, the time it will take to actually compute the Sibson interpolant will either be extremely huge or acceptable. Okay, so some thinking invested into the data structure will pay off later, okay, and when you actually use it for computation. All right, so the next big topic is least squares approximation. I want to talk about that. It's a big topic. There are entire books written about this, okay, and I only take the time to talk about this huge topic and tremendously important topic for scientific data visualization and their processing. I take only 2 lectures for that, right? It deserves much more, but you have to read the books tonight. So least squares approximation. Of course, the original treatise or paper about this goes back about nearly 300 years or so. Goes back to Gauss, so you have to start there. It's in Latin, so you have to read, of course, Carl Friedrich Gauss. Okay, he's 10 generations removed from me. Okay, he was my grandfather's 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 grandfather. Okay, that's 5 times 10 to 10 generations. So. What was the original motivation to come up with this issue of least squares fitting? The issue goes back to noise, how to handle noise in data. You know that a certain particular geometrical primitive or a certain physical phenomenon just has to be a line or has to be of a linear type. It varies linearly, right? So when you know that certain measurements are measurements of a phenomenon that must, based on physical law, behave like a linear function, like a quadratic function, like a cubic function, then you force that linear, quadratic, or cubic nature onto the formula that you compute from your measurements, period. Okay? So, of course, your measurement devices always introduce noise. So that's where it comes from. You have noisy data, or data that carry some level of uncertainty, that have to be made fit to a particular overarching physical law, which says it has to be linear, it has to be quadratic, it has to be cubic, a phenomenon, and therefore you just force that model onto the measurements. Okay? And then you want to do that in an optimal way, and the optimal way leads to this solution that is called least squares. So you can say in general sense handling noisy data. Okay? Handling noisy data. But that's just one way to look at it. Handling noisy data that must obey a specific function type. So, one example, you take measurements, and since your measurement device produces error, and even though you know that all these measurements should lie on a line, they will not line up perfectly lying on a line. So then you want to construct the best possible line that you can think of, that you can compute, that hopefully is unique, and this method produces indeed the unique one that is the best, the optimal solution for the least squares problem. So this would be a side xi. You have a measurement there, an fi, and this line would just be, I call it A for approximation, approximation of x, or just A of x. And in this case, if it should be a line fit, it is just of the form, it's an A times x plus b, right? Very simple. And I want to compute, well, the unknowns, the A and the B, given a gazillion measurements, sides and sticks. So another thing is you might know that a certain phenomenon just based on physical law has to be quadratic. And now you take certain measurements of things falling down and being exposed to gravitational forces, and there's some kind of quadratic law coming in. But anyway, your measurements, even though they should perfectly lie on one parabola, they do not perfectly lie on a parabola, but you force the best possible parabola you can construct for the set of measurements, okay? And again, this is the best parabola you can fit. So where's the least squares, or where are the squares? These are the distances or differences, okay, between the original value, fi, and the value of the line at the same location. That's where the difference, or the distance comes in. So this is the original measurement, the bullet, and this guy there is A, the approximation at that location, which differs from fi. And so then there is a difference, okay, a difference, di, which is fi minus A at xi. So here's the same principle. You have a location xi, you have a measurement, and you consider all these differences or distances, di, between the original measurement and the approximating function's value at the same location. So here, if this is a parabola, you would want to construct an A of x that is of the general form ax squared plus by plus bx plus c. And you have three unknowns to solve. Okay, so then that's what you do. So least squares, least obviously says something should be minimized, and there is an error function. And what you want to minimize in this case is the sum total of all the squares between these lines that you construct and the original height values. So one way to construct define an error function would be error as the sum total. Say there are n of those values, I from 1 to n. From 1 to n, no, let me start from 0 from now on. 0 to n of the differences. The differences are the fi's minus the approximations at the xi locations squared. Okay. So then this is the error function is a function of, well, of the unknown coefficients a and b. Right? You want to optimize this function subject to a and b being the varying parameters. That means, well, if you want to optimize E, a necessary condition for that function to be extremal is that its partial derivatives have to be 0 there, right? Something is extremal when the slope is 0. Derivative has to be 0. So if it's a bivariate function, A and B, we have to differentiate this thing with respect to A and B and set that to 0. Necessary condition for E to be extremal is that the partial derivative with respect to A of E is 0 and the partial derivative with respect to B of E is 0. Okay? And now you can actually plug all the terms in there and you can do a lot of math and algebra and you can use Mathematica or whatever you like in terms of a symbolic software package, and the result will be, well, the result will be the least squares solution for that. Okay? So the result will be the least squares solution for the discrete case. Least squares solution for the discrete case. I come back to that, what that means for the discrete case. And I will not derive the algebra, right? I mean, via algebra, that solution, but I just go back to the way I introduced this before. We just attempt to have a line that goes through all the points. Such a line doesn't exist, of course, in general, right? Unless the sticks really lie on a line. So we just write this down as interpolation conditions. This line, please fit all the given measurements and go through there. We know that it's not possible, we write it down that way anyway. So solution, if we write this down, we would have a times x0 plus b equals f0 until a times xn plus b equals fn, right? So those are the governing equations. So we have x0, 1 times ab equals first value, f0. Okay. A times x0 plus b equals f0, and now we go through all the sides, and the last side would be xn. So a times xn plus 1 times b equals last function value, fn. But that's not the solution. That solution is multiplying this by the transpose of that matrix x0, 1, xn, 1 times that matrix. Okay. And this matrix also has to be in front of the right-hand side. Okay, so this is now x1, 1, x0, 1, xn, 1 times f0 up to fn. Okay, so you can just say this is a matrix transpose times that original matrix times the coefficient vector, just call it coefficient vector c, equals m transpose times the f function value vector f. And so this m transpose times m will just be a 2 by 2 matrix, right? It's a small problem. The only cost that you have there is to multiply these matrix products. This row times that column, this row, and so forth, right? So this is very nice, solvable, unique, optimal, okay, and efficient. Why did I call it the discrete case? The discrete case for least squares approximation. If there is a discrete version of something, there must also be the continuous version, right? What is discrete here, or finite? The sides, right? The sides go from x0 to xn. Instead of using a line to approximate a bunch of 6, you can also use a line to approximate a function. Right? That's a continuous case. So, and that's the other very important aspect, to approximate a given function in a least squares sense by other functions. Why is that important? This comes from the world of observation and measurement, right? You take a bunch of measurements, your measurement device isn't good, and you need to fit a perfect physical or mathematical model to your data, and you force it, right, to be of a certain particular polynomial type, say, or sine function type, depending on the phenomenon. And you get these equations, you get the best possible solution. Now, why do you sometimes need to approximate very complicated functions with other functions? Which of your toys that you have in your rucksacks are doing that, are approximating some functions by other functions? Your calculators, right? Your laptops, your computers do that. Some functions are extremely complicated or difficult to evaluate, but if you're only interested in 10 decimal points, you can replace that original function by an approximating function, okay? That's one way to justify or to motivate the usage of least squares approximation in the continuous case or continual case. So, also, least squares approximation of functions. Least squares approximation of functions. Okay. Why are we particularly interested in that as computer graphics or computer visualization people? We want things to be fast, right, and efficient. Okay, so we need to approximate something that is complicated, or expensive to store, expensive to evaluate, by something that is simple, coarser, faster to evaluate, whatever, right? So therefore, when we have to deal with very complicated functions, then we also would like to replace it with simpler functions, right, that we can process much more efficiently. Of course, ultimately, you can say all we do in computer graphics and visualization is handling the discrete case anyway, right? We only have finite pointers anyway, so who cares? Can you make that argument is valid? So, what is this case? In this case, going back to my example over there, we have an interval f and a function that is nearly a line, but not quite a line, right? Right? A very complicated thing. We don't want to deal with this complicated thing, nor do we want to store it as a huge Taylor expansion or Fourier expansion. We just want to represent it by a nice, beautiful line, okay, over this interval. So now we have the approximating function a of x, and it is over some kind of interval from a to b. And this was the original function. Now it's no longer a set of fi values, but it's a function in its own right, f of x. Okay, signal observed, interpreted as a function, continuous function. And then you have something here that might be similar to a parabola, but not quite a parabola. Okay? So then you want to fit the best possible parabola through that somewhat oscillating, noisy signal. So here you have the approximating function, the a of x, and this was the original signal, the function, f of x. And you want to approximate it over a particular interval, right? Let's say from here to here you want to compute that best approximation. So what has to change when you go from something that is finite dimensional, to something that is infinite, continuous, and functional? So what has to be replaced now? Here you wanted to minimize something that related to the distances between the original value and the approximating value at the sites, right? Then you have to replace this by what? Here you minimize the sum, so the sum becomes what in the continuous case? Sum is, what is it? Becomes the integral, right? So a finite number of sites or locations where to compare becomes an infinite number of sites, right? Namely becomes this real interval from a to b over which I compute the error and want to minimize it, right? So this is the error, right? Or this is a representation of the error, okay? So error here is, of course, the integral. If I wanted to be strict, I have to say it has to be the L2 norm-based error, where I would have to have a square root there, but I don't like that. I don't want to deal with the square root, so I just talk about, take the square root away. This is a good enough an error. I just take the error from a to b of the differences of these two functions. The original one, the given one, f of x, and minus the approximating function, a of x. And I square that, okay? dx. And I want to set this to an extremal value, a minimal value, to get the best one. Okay, so if this particular function here was of the type a of x equals ax squared plus bx plus c, then, well, what would this integrand be? This integrand b would be that expression f of x minus, well, what is a of x? A of x is a times x squared plus bx plus c squared dx. Okay, I have to minimize that. And again, the degrees of freedom for which I have to solve this are these coefficients a, b, and c, right? The best possible parameters controlling the shape of that parabola. That's what I want to solve for. I will hit a little bit on this mathematics that is related to constructing these best approximations. This is related to linear spaces, vector spaces, scalar products or inner products, orthogonal basis functions, normalized basis functions, etc., etc. And I think all of you have come across these types of things in linear algebra, right? We all have to take linear algebra, right? Okay. So this all comes together now with linear algebra. And so probably in linear algebra you talked about vectors, right? Arrows on x, y, z, and 3 vectors and all of that, and inner products, computing angles, and scalar products, and you're computing the lengths of these things, and what is the coordinate system, the right-handed coordinate system, and orthogonal basis set, and all of that, right? So now we have to, there's the same machinery also works for function spaces, and I realize that not all of you have seen this before, so I will just hit on it. Okay, if something comes across very enigmatically or right, like a puzzle, look it up. And you will find it in books on numerical analysis and splines and approximation theory, okay? So you have to read these books tonight. So it's numerical analysis Then you have to read this book, Approximation and Interpolation by Phil Davis, of course. Approximation and Interpolation. By Phil Davis. And you have to read these spline literature. And much more. So what I put on the board is really colloquial English. There's a bunch of definitions that go before. I have to say something like this. Let bi from, say, 0 to n be a basis of a linear vector space of functions then a given function f of x. I only talk the univariate case. A given function f of x is optimally approximated by a linear combination of the bi functions, by a linear combination of the basis functions, the basis functions fcts bi of x, when the coefficients ci of this combination satisfy the following equation of this combination satisfy and I will do an example for this, and then it becomes very clear what it means. Okay, in the end, everything is very clear. I don't like this dialect, by the way. Okay, when I talk this way, I don't like this. You start with definition, completely abstract, no picture, no nothing, no motivation. It's very abstract, right? Where's the picture? We are in graphics. You can have a bunch of definitions, a bunch of theorems, and a bunch of lemmata going along with them, and maybe at the end of the day, maybe there's a figure like that. Maybe. Charles Toohey, who writes his books about spline theory, he likes to write his books 500 pages long without a single picture. He says pictures are not good. You should avoid pictures. Don't make pictures. That's everything algebraically. I don't like that. I'm graphics. Right? I come from art. So I like pictures. I don't have a great deep understanding of mathematics. I'm happy when I understand the very trivial mathematics that we need for graphics and visualization. So anyway, this is all I can do. I give you the solution to this stuff, and then I go very quickly back to some pictures and a very simple example. Because it all comes from very simple, trivial application, and then the people lift it to a very general framework. So there are inner products. I also have to define those actually. So these basis functions get multiplied, b0, b0. These expressions are inner products of those basis functions. b0, b0, bam, bam, bam. The last one would be b0 dotted with bn. And then bam, 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 bam. The inner products here are bn, b0, and then the last one has to be the basis function bn, inner product with itself, bn, bn. The unknown coefficients in the expansion are then coefficient 0 up to coefficient n satisfy to be equal to the inner products between the given function f and the individual basis functions. B0, blah, 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 blah. The last one is the inner product between the function and Bn. All right, where denotes the inner product of two functions FCTS f and g as where denotes as blah 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 f comma g is integral f times g dx. Bam bam bam. I want to stop there. And I want to go straight into the application and the relevance of this approximation theory for our purposes, namely for approximating in very simple ways complicated functions. We need to use this beautiful machinery, beautiful theory for the construction of so-called hierarchical or multi-resolution spline approximations of complicated functions. Construction of hierarchical slash multi-resolution spline approximations of large data sets slash complicated functions, of large data sets slash complicated functions. Okay, and let's start with the simplest example. There's an inductive way for teaching and there's a deductive way for teaching, right? I think usually one sees professors teaching one style or the other style, right? I mean, inductive approach to teaching is to usually present the general, to introduce the general theory with very simple, easily understood examples first. You throw a bunch of simple examples, simple pictures on the board, and you begin to see the more general underlying theory, pattern, rules that governs all of that. I like to do it that way, okay, in general. Start with something very simple, make a picture, explain things on the, right, for the simple example, and then arrive at the general theory. Some other professors like to do it the other way. They start with, right, throwing the general framework at you right away, boom, here it is, for n dimensions, arbitrary case, boom, 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 without making the picture. And later on, right, in lecture number 17, there will be a picture, if ever, right? And so, but I think we as computer graphics professors or visualization professors have this wonderful advantage to introduce many of these very complicated concepts by making simple pictures. And so we have to do that. So when I took my mathematics course, it was quite different. Okay, so I have both. I mean, I was trained in both. Okay, so I see the different approaches. So, and that's also great, I think, about graphics and visualization, that you can combine rigorous mathematical theory and training with beautiful, even artistic, right, expression. Right? And you can combine that. Right? The very rigorous, solid, and foundation-based theory of mathematics with ultimately artistic expression, and then go in between. Right? It's very nice. So one day when you will have to develop your teaching style, right, and you will stand before a group and will teach, then you will have to make a choice, right? Whether you want to come in as the artist, right, teaching all of this from the artistic perspective, or from the very rigorous mathematical, theoretical perspective, or somewhere in between. So, sorry, I was wandering off. So, usage example. Example. There's this concept of spline that I was hitting on. Spline approximations and complicated functions or functions, right? So a spline means we represent something with multiple pieces. Example is I use a constant spline. A constant spline approximation. In a sense, any computer display is a constant spline approximation because you have pixels and you have a constant color per pixel. Okay, so that's really all we do. So, all right. So we need the basis functions. I talked about these mysterious basis functions, bi over there. Basis functions can be of unit length, right? When is a function of unit length? Okay, again, go to your linear algebra books. There will be examples in there, hopefully, talking about the functions as well. And then when are two functions orthogonal to each other and all of that. I guess hopefully in there too. The simplest function type is these guys, box functions. Okay. So say I have 3 happy boxes. Okay. And I make it even simpler. So I say this is x naught, this is 0, this is value 1, this is Cartesian, right? 2, and this is value 3. And I have an x, and I have a signal or a function. I have some kind of function. Okay, this is my given f of x. And over this particular interval, from a to b, right, this is my beginning from a to b, I would like to approximate this guy, this function, with 3 pieces. That's what you do when you rasterize something, right? You will just evaluate this function there, there, and there. And then you give this pixel that constant color everywhere in that pixel region. You evaluate it here, and then, okay. But the function is more complicated. So how do you do that? So I said these are unit functions. So this is 1. Okay. This would be my basis functions, a box function. This would be my basis functions b0 of x. This would be my basis function. Well, it's a representation of those functions. b1 of x, and this would be my b2 of x. Right? They are 1 inside these unit intervals from 0 to 1, the other one from 1 to 2, the other one from 2 to 3. And now, these functions are also nice. Why are they nice? Because they are of unit norm and because they are orthogonal to each other. Huh? So we want to construct a constant spline of the type, okay, so this spline is our approximation, right? We want to construct an approximation over this interval from a to b, which will be a linear combination of these basis functions. Huh? Something times this guy, plus something times this guy, plus something times that guy. That's what we want to compute. We want to construct some. We have 3, I from 0 to 2. We don't have the coefficients, ci times these box functions, bi of x. Okay. The picture says what the box functions are. They are 1 over an interval of length 1, and they are 0 everywhere else. And so I'm going to say that these guys are nice because they are orthogonal, right? Bi dotted with Bj, or inner product of Bi times Bj is, well, I'll spell it out. It is 1 if I equals j, and it's 0 otherwise. Okay, let's make them orthogonal. Right, this dot product again for functions is defined over via that integral. And the other thing is they are also of length 1 or of norm 1 in the L2 norm sense. That means the length. Okay, this is the length of the norm, the L2 norm of a function of any of these Bi's is 1. Okay, so that means this means they are orthogonal, ortho, linearly independent, pairwise, and they are here. This means they are of unit length, or they are normalized. Okay. What do we need to determine? We determine the CI values, right? So the CI values come from this general apparatus, right? This is the general machinery. So I write this general machinery down for this very trivial case of approximating a function with just a linear combination of three box functions. Okay, so I have to solve this thing, right? I have to compute the elements of a 3x3 matrix. So that would be box 0 times box 0, box 0 and box 1. Basis function b0 dotted with b2. And then last line is b2 dotted with b0. And then last entry is box function b2 dotted with itself, b2. Okay, there's always a comma there, right? You know it. And then there are the unknown coefficients, c0, c1, c2. And then on the right-hand side, I have to compute inner products between the given signal, f and the basis functions, f and b0, f and b1, and f dotted with b2. Okay. And now, what put this down, these nice conditions here, right, that these basis functions satisfy. It makes everything very nice because it simplifies that matrix greatly. When you compute the inner products of certain vectors or functions that are standing orthogonally on top of each other, then what does it mean for the inner product? Huh? Two orthogonal vectors have what scalar product or inner product? Yes? Be brave. 0. Right. So this matrix is just filled with zeros. Right? Everywhere, except maybe somewhere. So when I dot this guy with any of the other functions, then the dot product is 0. Except when I'm computing the inner product of any of these guys with itself, right? And then it is 1 because they have this area 1. Even when I take the square root of that area, I would forget about the square root. So only the main diagonals are 1. Only the main diagonal is full. This is just 1. This is really nice. So this becomes, in this case, this is 1, 0, 0, 0, 1, 0. 0, 0, 1 times the unknown vectors, coefficient vector, c0, c1, c2, equals, and now you have to, I have to write down the definition of these inner products. The function f is an arbitrary function, right? F is anything, so I cannot replace it, but I cannot make any assumption there. So I really have to write down what it is. The first inner product will be the integral from 0 to 1 of given function f times basis function 0 dx. The second inner product will be the integral from 1 to 2 of the given function there times basis function b1 dx. The last inner product will be the integral from 2 to 3 of the given function times basis function 2 dx. Okay. Now I don't have to solve a matrix problem at all. I have the coefficients there. But why do I do this simple motivating example? Because very soon we will come to linear splines and quadratic splines and cubic splines, okay? But you understand the whole machinery just by looking at this. So this means C0 is just this integral from 0 to 1 of the given function to be approximated times the basis function there, B0. Well, of course, I put the argument there, so I don't have to put the argument there. You know that these are functions. So C1 is the integral over the next interval, f times b1 dx. And you have to tell me what these integrals are. What is the meaning, the geometrical meaning of this integral? So that's all that it boils down to. C2 equals 2 to 3 function times basis 2 dx. What is the meaning of an integral? Oh, I can forget this, right, actually. I don't have to say times b0. Why can I forget that? What is the value of b0? It's 1, right? It's even simpler. It is really just, this is really just the integral from 0 to 1 of the function, f dx. This is really just the integral from 1 to 2 of the given function, dx. And this is really just the integral from 2 to 3 of the function, dx. So what does it mean? The coefficients are nothing but this is just the meaning of an integral. The meaning of an integral of a function is what?
The area.
The average. Okay? If I give you any interval and I give you a function, okay, then the integral of this function, from here to here, is nothing but the average function value over this span. So the average function value is something like that. Huh? Okay, so what does it mean? What have we computed? We have computed a bar diagram. That's all we are doing. We are computing a bar diagram for this, okay, over this range. Huh? So from here to here, right, we replace the smooth function by 3 bars. Huh? And the interpretation of the integral, this is the integral of f over this range. It sums up all the values and divides by the length of and gives you the average height. That's what the meaning is. So the first thing will be, the first coefficient will be the weight, the coefficient that multiplies this bar and lifts it up. C0 times its bar. Initially the bar has a height of 1. Now you multiply it by, well, the average value there. Okay, it is something like this. Okay. Now you go to the next interval. Coefficient number 1 is a factor that goes before this box. So it will be the average here, something like that. And then the last one will be the integral of the function from here to here, and the average is somewhat like that. Okay. So what is the outcome? The outcome is this representation, right? Right? It's step function. So this is the best possible representation of this function using 3 steps and 3 bars. So it satisfies this entire machinery. All the rules and steps of the general machinery come into play. And what results? Well, the result is we just have to compute averages of functions over certain intervals. So now I have to do this for the much more interesting case of linear splines. And then as homework, you can do it for cubic splines. So box functions will now become head functions. Next, well, we like linear approximation, right? Piecewise linear approximation is linear spline approximation. So linear splines. Linear splines. All one needs to understand really is the basis functions. The rest is trivial. So a motivating example, what I'm after this. the goal. The goal will be a sequence of increasingly better linear splines. Sequence of increasingly better linear splines. And again, I first start with a simple picture to explain the goal, and then I do a simple example. So, one x, let's see, another one, x, another one. It gets better and better. Say you have a function that behaves like this, okay, and you want to approximate it with a linear spline. The simplest linear spline will just will attempt to approximate that function with one line segment. Can we do that? Well, we have done this before, okay? The best possible line over this particular interval is probably something like this. Well, this is probably the best line you can construct for that. Okay. Now, if you can approximate this complicated geometry, this complicated graph, this complicated function with one line, then you can also approximate it with two lines, right? So the next thing is, well, increasingly better splines going from one segment to two segments. Okay, so you have the same function that you want to approximate, this behavior, and now you use two segments over the same interval from here to here. Now you use two lines. Okay, your IC set has to behave something like this, right? A line and another line. So I always like to use the point in the middle because it's simplest to begin with. Okay, so I want a line here and I want a line here. But I also want these lines to snap. There's a constraint. I want them to be connected. So the result should be something like this. Okay, bop, and then bop. Okay. So this is a two-segment or two lines here, a two-line best linear spline approximation. And from that, I want to go, well, from 1 to 2 to 4 intervals, right? Approximate this guy over 4 intervals of same length. Okay, so here, from here to here, and represent the domain by 4 subintervals of equal width, and then compute 4 segments that, again, all snap together, all come together, and approximate this wild shape as best as I can. So then it's probably like this. And you see it gets very nice very quickly. Okay. So where are the basis functions? Now I also draw the basis functions. As I said, only thing that one needs to understand are the basis functions and how they relate to these splines. So initially, I just use two head functions. One starts at 1 and goes down, and the other one starts at 0 and goes up. Okay? I call this location 0 or not 0, and this is location 1. So this guy has its maximum or its 1 value here, so I call this guy head function 0 of x, and this one is head function 1 of x. Now here I have more head functions. I have one head function that starts here and goes down, the other head function goes up and goes down, and the other one starts here and goes up. So again, the numbering is the same, x0, x1, x2. We have one more knot, and this guy would be head function 0. This guy here would be head function 1, and this guy here is head function 2. Okay. All right, now here I have many more head functions. So the first one is centered here at x0. Here's x1, here's x2, here's x3, here's x4. So I have a bunch of head functions. So this one goes down, the next one goes up, goes down, the next one goes up, goes down, next one goes up, goes down, and the last one just goes up. So again, these guys get their index based on their location, where they have maximal value, right? So this head is head 1 because it lives above x1. This guy is head function 3 because it lives above x3. So this guy is head 0. This guy is head 1. This guy is head function 2. This guy is head function 3. And this guy is head function 4. And what do we construct? We construct this guy as a linear combination. It's a linear function. So the approximating function here, a of x, is a sum, I from 0 to 1, of unknown coefficients, ci, times the head functions, times hi of x. Right? This value here will be the unknown value, c0. This height here, this value, will be the value c1 that we have to compute. But same here, now I just put it here on the last one. So this one will be the approximating function a of x, which is a combination, a linear combination, coefficients unknown, times the head functions hi of x. And in this case, there are 5 from 0 to 4, I from 0 to 4. And the coefficients ci are unknown. And again, these height values, where these bullets are the values of the coefficients. So this one is c0, this one is c1, and this one will be c4, and so forth. And this one is c3, and this one is c2. Okay. So what's given, what's to be computed? Well, we are given the function to approximate, and we are given, implicitly, this basis set, the basis functions, which are head functions, and we need to compute the coefficients from c0 to cn minus 1, right? c1, c2. Okay. Again, to obtain the unknown coefficients, the unknown coefficient ci, for the optimal linear spline, and that's important, the optimal, there's no better one, that makes it so nice, for the optimal linear spline, to obtain unknown coefficients, one must solve let me stay specific to this example, okay? Otherwise, I end up with huge matrices. So in this case, what do I have to solve? I have to compute the inner products of these basis functions. Right? So they are now the head functions, and the way I've numbered them, I start at 0. Head function 0 with head function 0. Bam, bam, bam. The last head function in this example is head function 4. So head function 0 dotted with head function 4. Well, the unknown coefficients in this case here go from C0 up to C4. C0 up to C4. And on the right-hand side, I have to compute inner products between the signal or the function to be approximated and the head functions, the basis functions. First one is the inner product between the given function f and the head function 0. And now I just fill in the rest. And filling in the rest means I end up with this guy, head function 4, dotted with all the others. Head function 4, inner product with h0, and head function 4, inner product with itself, h4. And here, the last one is the function, inner product with head function 4.
Professor?
Yes?
Does the literature explain a head function?
Oh, these are colloquial terms.
What's a head function?
Box functions, head functions. There are strange names for many different basis functions. There are also Mexican head functions. There are all kinds of things when they're always widely oscillatable. These basis functions have strange names. It's just a funny way of naming them. Yeah. So this is a head function. So a Mexican head function looks like this. Goes down. Okay. So I didn't come up with these names. But also in the electrical engineering literature, they come up these words. Fourier transform, signal processing, and all of that. That's where this comes from. Words of this. But now we have to solve this, and then I will stop. Now we have to solve this, right, for this case. Before, I solved this for the most trivial of cases, where we ended up just having a bunch of ones in the remainder organelle. The question is, now I go to the next more complicated case, namely from constant to linear. Do I have to deal with a full-blown matrix, or is it still relatively simple, a matrix that I have to handle? It all boils down to the degree of, the way these basis functions overlap and produce non-zero or zero inner products. Okay, that's the issue. Do many of these inner products vanish? What about these heads? The heads are different from zero only in two intervals, right? So, for example, when I take this head function and compute its inner product with this head function, meaning I take the product of these guys and compute the integral, well, the product of these guys will be what? It's zero. They don't overlap in the domain, right? So this guy here, H1, will have non-zero inner products only with H0, with itself, and with H2. None of the others, which are far further away, right? Okay, so this makes this very nice. Specifically, one obtains I put this for context there. Basis functions. As I said, everything relates just to the basis functions. And I have to give this now the general setting, but that doesn't make it much more difficult. 1, 2, 3. The delta, there's a spacing between these. Okay, I make this now arbitrary, no longer an integer. So this is your x0, this is your x1, this is your x2, your x3, and your x4. Okay, and so the head functions look like this. This one goes down, this one goes up and goes down, this one goes up and goes down, this one goes up and this goes down, and this one goes up. Okay, so these are the head functions over a non-uniform, not set. And so you have deltas here, right? So this would be the deltas. I want to name them too. These are the length of these intervals, and they are not of the same length. So this would be a delta 0, this would be a delta 1, this would be a delta 2, this would be a delta 3. Again, this guy would be H0, this guy would be H1, this one is H2, here we have H3, and this guy is H4. And what you get is really beautiful. Okay, you get the unknown coefficient vector, C0, C1, C2, C3, C4 equals H0 has a non-zero inner product only with itself and with H1. But all the other inner products with all the other functions to the right are 0 because they don't overlap. Okay. So you will only have this structure. That will be the structure of the matrix. Now I just have to give you the rest is 0. And now I just have to give you the values for that. What the values are. And the values are combinations of the deltas. So the first one would be 2 delta 0 and delta 0. The next entry would be delta 0, 2 delta 0 plus delta 1 and the delta 1. The next entry would be delta 1, 2 delta 1 plus delta 2 and a delta 2. The third entry would be a delta 2, a 2 delta 2 plus delta 3 and a delta 3. And the last row would be, of course, a delta 3 and a 2 times delta 3. Okay, and so the rest is all just zeros. Okay, this is really beautiful. And do not memorize these things. I mean, don't get scared, okay? And you don't have to memorize this either. It's all about patterns. Right? This is all about pattern. And you see what I did here, right? I just took these deltas from left to right and then put them into the organelle, right? I didn't compute this on the fly. I knew what the pattern was. I remembered the pattern before. So and then the index comes automatically. So 5 by 5 matrix, 5 unknowns, and on the right-hand side I have 6 times. Don't forget the 6 times, very important. 6 times. 6 times inner product between I have to spell this out now, right? It's the integral from x0 to x1 of the function f times the head function 0, right? dx. I make it explicit. The next one would be whatever, and the last one would be the integral. The last one is integral from, what is it? The last one goes from x3 to x4, x3 to x4 of function times head 4 dx. Okay. Well, I should do the second one too, so you see it changes a little bit when you go to the next one, right? When you go to the next one, this next head function is different from 0 over 2 integrals, so it has to go from x0 to x2. So the next one is from x0 to x2 of f times head function 1 of dx, right? So the integration limits or boundaries are always, well, the domain of one of those heads. Is this a nice matrix or not? Before I had a matrix there where I only had ones in the middle, right, in the diagonal. It was the most beautiful matrix, right? Because I didn't have to do with the matrix. I didn't have to do anything with the matrix. It was already solved, right? Huh? The coefficients were whatever was on the right-hand side. Do I have the same case here? Anyone remembers what this type of matrix is called? Anyone taking Professor Bai's class by any chance?
It's tridiagonal.
Yes. Yes. It's a bent matrix, right? With 3 diagonals being different from 0. This is a beautiful tridiagonal matrix, and we all love them. Diagonal matrix. Why do we like it? Huh? Because you can solve this in a full-blown matrix. Requires order of n cubed multiplications, right? But a bent diagonal matrix requires order of n rows and columns, order of n computations, okay, multiplications. That is good. So we like that. Okay, very happy about that. Now I give you even the more specific solution for that. When this becomes a uniform knot setting, when these are actually uniform knots, just want to put this on the board so you have seen that. You have this in your notes because it's so really beautiful. And you will have seen this matrix before in different contexts. Now you know where it comes from. Specific case is when you have x0, or the xi's define a Cartesian mesh, right? x0 is 0, x1 equals 1, x2 equals 2, and so forth. And for this particular case, I from 0 to 4, why don't you want to stick to this guy? So when you get a beautiful, simple solution, you get 2, 1, 1, 4. Let's see. 2, 4, 2, 1, 2, 4, 2, 2, 4, 2, 2, 4, 2, 2, 1. And the coefficients C0 up to C4 equals 6 times these other guys, okay? But you have seen this matrix before. I'm sure you have seen that. This matrix comes up all over the place. Also in Professor Bai's class. Yes? Where does this 6 come from? Do I have it in my notes? Do I have it in my notes? Let's see whether I can answer his question. Where does the 6 come from? You don't like the 6? 1, 2, 1, yes, that's good. Error, there is an error. Okay. Okay. Don't copy me always. Don't copy me at all, just think. So these are the ones I confused myself. Okay. If you don't like the 6 on the right hand side, divide everything by 6 and the 6 is gone. It comes from these guys. When you actually compute these things, these integrals, they are fractions. Okay? When I compute these things first, then everything would be 6th. This would be 4/6. This would be 1/6. And because I don't want to divide by 6, I multiply the left and the right hand side by 6. Okay? Because I want to have integers on the left hand in the matrix. That's why I multiply by 6. When you actually compute these inner products, these integrals, for these head functions, you get 6th. Okay? So that's when you multiply both sides. So in the textbooks, you see this. And this matrix in particular shows up in a gazillion of applications, and this is one way to really get to it and see where it comes from. Great. Have a good evening. I see you Thursday.